we can see Okay, good morning, everybody. We'll get started in about a minute. Okay, I think we can get started. So good morning, everybody. My name is James Lamb. I'm an engineer at a company called Saturn Cloud. And I'm here today to talk to you about scaling machine learning with Python and Dask. You can look into the work that I've done at my GitHub here, contact me on Twitter, and I'll share all this contact information at the end of the talk as well. So let's get started. Okay, so first I want to offer a disclaimer. So I have a vested interest in Dask. I'm an engineer at this company, Saturn Cloud, where we're working on a managed Dask and Kubernetes offering. So this talk is not going to be a Saturn Cloud sales talk. You should come check us out if you're interested in Dask after the end of this talk. Okay, so the way that I'd like to run this talk is in the first half of the kind of me talking from slides part, I want to explain why Dask. Why does something like Dask even exist? In the second part, we'll go a little bit deeper into what Dask does, how it works. And then in the second half of the talk, I will code on screen, as scary as that is. I'll run some stuff, and I'll show you Dask in action out on AWS. So let's start with why Dask. Let's start with Python. So data scientists love Python. For those of you who were in Mariano's talk right before me, you saw him using a lot of the tools that are listed here. You saw him using matplotlib and pandas and numpy. You saw him working in Jupyter notebooks. Python has really established itself as a popular ecosystem of tools for data science work, especially for data visualization, data exploration, and machine learning. So Python is awesome. It has this very vibrant community maintaining these libraries, and people really like to work with these libraries. They've really gotten used to the APIs for these libraries. However, most of the popular data science libraries in Python were only designed to work on a single machine. So they weren't built with distributed computing in mind. They were built to kind of manage their memory model assumes that all of your data is kind of in one physical machine, and they don't tend to have kind of first-class support for distributing work across multiple machines. And what that means is there's an upper limit on the size of data set or the size of problem, size of idea that you can explore with these libraries. So as an example, if you have ever used pandas and you haven't read this blog post, 10 Things I Hate About Pandas by Wes McKinney, I really recommend it. In that blog post from a couple years ago, Wes talks about some of the features of pandas that make it maybe difficult to use and make it difficult to scale to larger problems. And some of the things he talks about in there were directly related to early inspiration for the Apache Arrow project. So the kind of overarching theme here is that for data science workflows, it's really easy to get to a point where you want to do more computation or you want to work on more data than maybe your typical laptop or your typical kind of reasonably priced VM in the cloud can work with. So as an example from pandas out of this blog post, Wes McKinney, the creator of pandas, says, you should expect to have 5 to 10 times as much RAM as the size of your data set just to work with pandas. So that can get pretty big pretty fast. And so when you get to this point, when you want to, when you're running up against a physical resource limit, you have a couple of options. One of those options, for the specific task of training machine learning models, one of those options is to use less data. And there are a ton of tools that will let you write queries at, kind of interactive level speeds over gigantic data sets. I've listed some of them here. There are dozens of them, hundreds of them. If that's not possible, maybe you can get away with what's called vertically scaling. Maybe you can get away with just buying a bigger machine. You can go out to AWS or Azure or GCP, and you can just get a larger machine, more memory, more CPU, do your work, and then spin that thing back down. But that's going to cost some money. And then one other option that you have is to use more machines. So this is why Apache Spark has been so popular. This is one of the benefits of using a project that can flexibly request resources in Kubernetes like Kubeflow. And it's one of the aims of projects like SageMaker, Ray, Dask. We're going to talk a lot more about these. But these are kind of your options when you get to the point where you're resource constrained. I also want to make the point here that when I talk about data science work or machine learning work for the rest of this talk, I'm specifically talking about training models. So that is doing hyperparameter tuning, feature engineering, and training models. So the whole world of serving models, scoring, that is totally separate from what I'm talking about. And the one moment in time data needs of that type of workflow tends to be a little bit smaller. Okay, so some machine learning frameworks actually have their own distributed training interfaces. So if you go out to work with XGBoost, LightGBM, TensorFlow, PyTorch, each of these projects, each of these frameworks, they've implemented their own distributed training interfaces. And so what does that mean? Distributed training means that your data set is physically separated across multiple machines. And it means that processes on each of those machines can each contribute something to the process of producing a model at the end. And that also means that each of these libraries, they've implemented their own code around retrying in the face of network delays, of how they want to pass packets back and forth, how they handle security, what their maximum message size is, all of these other kind of like network communication problems that are not really the core value proposition for a project like LightGBM, for a project like XGBoost. But those options do exist if you can kind of fit your modeling problem into one of these frameworks. However, most of the work there is around training, and it's around experimentation. And so that means that if you need to do very, very custom work to generate your data set in the first place, to do your feature engineering, to get the data from the internet or something like that, you'll find that you have to think really hard about how each of these distributed training interfaces works, and be sure to produce a data set that will kind of fit into their expectations. And each of their expectations is a little bit different. So this is why many people turn to more general purpose distributed computing frameworks like Apache Spark and Dask. So both Apache Spark and Dask, and there are other frameworks, provide this popular, well-tested, general purpose way to use multiple machines to accomplish data science tasks. So data science tasks is like summarize this tabular data set, train a machine learning model on this data set, train many different machine learning models with different hyperparameters, tasks like this. And there are a lot of ways that Spark and Dask are very similar. Both projects have permissive open source licenses. Both projects have kind of very vibrant open source communities. And then in terms of their machine learning features, they have some similarities. So both of them have first-class support for distributed training in Spark. You may have used Spark MLlib or Spark ML. There's a project from Microsoft called MML Spark that seeks to give you access to more different types of machine learning algorithms. But in that case, distributed training means that if you have multiple machines in your Spark cluster, all of them can contribute something to training a model. And that allows you to work with larger data sets or to train more models. Both projects also have distributed data structures. So a distributed data structure, you may be familiar with the Spark RDD, or maybe you've worked with a Dask data frame before. In a distributed data structure, you code against it, and you'll see this in the code that I show in a little bit. You code against it as if it's one data structure living in memory on your laptop. And the library handles the details of the fact that it's actually many, many little pieces of that data structure spread over possibly many machines. And the library will kind of allow you to query against that data, add columns to it, transpose it, manipulate it without needing to know about each of those individual machines. So in these ways, Spark and Dask are really similar to each other. But there are some differences. So let me start with how Dask might be different from Spark in a way that is appealing. So first, Dask is a Python-first project. Dask is written in Python, and it generally is expected to work well with other languages that Python interfaces natively with. So it's kind of like a dirty secret of data science code that when you work in Python and R, a decent percentage of your the actual code in those libraries is C and C++ and Fortran. If you ask any of the people at like the Julia conferences, they will proudly show you their table of how much of Python and R are actually C and C++. But so what that means is Dask, you know, Dask is really made for Python developers, data scientists who are working in Python. And the Dask project, the maintainers there are the maintainers from other popular PyData libraries. They are the maintainers from the Jupyter project and from Pandas and from other projects. And they try to maintain this API parity with those PyData libraries. So you'll see in a little bit when I show you some code that when you write a Dask data frame, when you work against a Dask data frame, for example, you don't feel like you're writing Dask code. You don't feel like you have to take your code that worked with Pandas and dramatically change it to work with Dask. They try really, really hard to keep the same API, the same familiar methods, and the same familiar kind of different classes, so that the transition from working on a smaller data set to working on distributed data structures is really, really easy. In Dask, you also have a lot finer grained control over the task graph. So both Dask and Spark, the way that they work is you describe some operations that you want to do, and then those are represented as an ordered graph that tracks the dependency between those operations. So, you know, the famous example is always like counting words in a stream of text, right? You have a bunch of tasks that each read in a chunk of the text. You have another task that then takes that data and finds all the words and counts them. And then maybe you combine all those counts from the different chunks and get kind of a global sum, something like that, right? You can envision that as an ordered graph where all of the reading tasks have to happen before the counting tasks. And that kind of reduction task at the end has to happen at the end. So both Dask and Spark do this. But in Spark, you're working at a higher level. So you're using these higher level operations kind of from functional programming like map and reduce and group by and things like that. And then because there's a slightly more rigid interface when you work with Spark, that means that in Spark, the Spark library has the ability to do some optimizations. They're able to kind of peek ahead the same way that say a query planner in a relational database peeks ahead at your SQL and say, oh, you know what, this one function call isn't actually relevant because there's this other filter that's going to drop all of that stuff anyway. In Dask, that's not going to happen. In Dask, Dask allows you much lower level access to the graph. And so that means that you can create more complex algorithms. It means you don't have to fit into the kind of map, reduce, filter, group by paradigm. But it also means that Dask is not going to be able to give you as many optimizations around the way that the graph is built as Spark does. And then finally, really, really important for data science, Dask has support natively for distributed multi-dimensional arrays. So in Spark MLlib, the matrix types that you can work with for your training data or your data that you're going to do batch scoring on or whatever has to be 2D data. That has to be kind of just rows and columns, but Dask can support the same interface as the popular NumPy project in Python. And so that means you can work with multi-dimensional data, which is really good for problems like computer vision, for example, when you're working with images. Okay. However, like I mentioned before, because Dask is so flexible, it does also lack some features that Spark has that have made Spark really popular. So my goal in this talk is not to convince you that Spark is dead. Spark is very, very, very much not dead. And some of those things, for example, so Apache Spark has a SQL engine. Maybe some of you watching have worked with Spark SQL and the SQL context and working with data frames. Dask does not have that. And you know, there have been projects to kind of bring that to Dask, but you should just, for now, conclude that Dask does not have a SQL engine. So you're not going to be able to write SQL over tabular data with Dask alone. There are definitely Dask plugins and things that are in development to be able to combine Dask with data warehouses like, say, Snowflake, but there's no native Dask SQL project that you could kind of compare apples to Spark SQL. Like I mentioned, Dask also does not have some of the higher level optimizations that you get out of Spark. So Dask is not going to be able to peek ahead at your graph and say, oh, you're doing this reduce by key at this stage, but I already know that you have this filter step up ahead where you filter down to only one key and it's the same key, so I'm just going to drop that reduce by key completely. Dask is not going to be able to do that kind of thing. Dask also does not have native support for graph data structures. So there's nothing in Dask that is equivalent to GraphX from the Apache Spark project. And then Dask is really not going to have support outside of Python, for languages outside of Python. So, if you have code that is a Python interface to other native code, if you have a Python, NumPy code that is calling C and C++, or PyArrow that's working with C++, you can definitely use those Python libraries, but there is no Dask for the JVM. There's no Dask R project. And, Dask doesn't really have as far as I know, any intention of adding those things. Dask is really focused on the PyData ecosystem. And you have to be working in Python if you're working in Dask. So for some of you who have existing code bases in, say, a JVM language or an R, that might be a downside. On the other hand, I think there's also a lot of benefit to that focus. It means that the developers working on Dask, they're working on features, they're working on hardening, they're working on security options, deployment options, and it means that they're now working on re-implementing the same features in multiple languages. Okay, I promise this is the only benchmark I'm going to show you, and it's okay if you don't believe in benchmarks in conference talks. I won't be offended. So at Saturn, we sell this managed Dask offering, and we also have this vested interest in improving the Dask ecosystem and driving adoption of Dask, whether or not that adoption is with us. And so we've done some work that is benchmarking work for machine learning workflows, where we've compared working with Dask to working with Spark ML, to working with kind of just scikit-learn on a single laptop. You can go, for example, to, oh, this is the wrong link. Okay, I'll be sure to share the link and how to get all of these slides at the end of the talk. I apologize. This is definitely not the link. But we've published a couple of articles where we've benchmarked the performance of Spark ML against Dask and against scikit-learn. And for example, we found in a project, we were doing a grid search over different values of the hyperparameters alpha and L1 ratio for an elastic net regression. And we found that Dask was more than 40 times faster than Spark. And that the scaling properties were a little bit better, and that both of them, to be fair, perform better than scikit-learn. So when I say Spark, I also specifically mean PySpark. So kind of the asterisk on everything I say about Dask versus Spark is assuming that you want to work in Python. Take that benchmark for what it is. You can do a lot of really cool stuff pretty fast in Dask. Okay, that is all that I want to say about Dask versus Spark. I am honestly not qualified. I don't know enough about Spark to give you a deep, should I use Dask, should I use Spark comparison. My pitch to you is, if you have a lot of Python code around, especially if it's PyData code like NumPy, Matplotlib, Pandas, scikit-learn, and you find yourself doing things like downsampling your data to fit it into a laptop, or running less experiments because your code's taking too long, I really think that you should consider Dask. And you can go to the Dask documentation for a more detailed comparison to Spark. Okay, next, let's talk a little bit about what Dask is and how it works, now that hopefully all of you are convinced and are Dask evangelists. Okay, perfect. All right, so Dask works great on one machine. You can use Dask as easily on well, not as easily. You can use Dask very easily on your laptop, and you only have to make very minimal code changes to go to a distributed setting. For this talk, we're at the Chicago Cloud Conference. I am not going to talk about anything that relates to using Dask on a single machine. So today, for the rest of this talk, I'm just going to be talking about Dask distributed, kind of working on multiple machines. So Dask is an ecosystem of many libraries. There are 50 plus repos in the Dask okay, it's 51. There's 51 repos in the Dask org in GitHub, and then there are other projects that are not necessarily in the Dask org. I'm going to try to give you a summary of some of those as I explain the ecosystem and as I explain kind of how this works. I'm going to use this notation with the square brackets and the purple text to say that I'm talking about a repo in Dask. Okay, so let's start with distributed. Distributed is a really, really important project from Dask, and this defines the interface for, the interface for your code in a Python session to talk to a Dask cluster that's made up of multiple physical machines that are all going to contribute to doing work. And so the way that this works is in your notebook, and you'll see this in the code that I show in the second half of the talk. In your notebook is considered the client. That client knows how to talk to a scheduler. So the scheduler, that is the thing that knows about the existence of all the workers. It knows the size of those workers. It knows something about their hardware. You know, it knows whether they have CPUs attached or GPUs attached. It knows about how much memory they have, things like that. And what happens is when you work in Dask, you use these different Dask libraries that create a task graph. That graph is submitted by the client to the scheduler. And then the scheduler inspects that graph, breaks up the work, and asks each of the workers to do different pieces of that work. And that's kind of when the graph gets executed. That's when your code gets run. Workers send back data, they send back task statuses, they send back logs, and the scheduler sends all those things back to the client. And so in that way, your client code never needs to know about individual workers. You never need to say, I'm going to schedule this work onto this specific node with this specific IP address. You just submit Python code to the scheduler, and the scheduler takes care of kind of managing all of that stuff. And the library where this is defined is a library called distributed. Let me take a sip of water. Okay, cool. So just to be clear, the scheduler and the workers, these are just Python processes. So you can create a 3-worker distributed, I'm using air quotes, cluster just on your laptop using these CLI commands, Dask scheduler and Dask worker. So when you think about the workers, when you think about the schedulers, just think about individual little, say, containers or VMs or bare metal machines or whatever that are running these processes and listening on these ports for information from the scheduler. Okay, now I'm going to take another sip of water while you read, then I'll explain each of these. Okay, let's talk about this. So I mentioned that distributed has kind of established the interface. It's established what it looks like to talk to a distributed Dask cluster. There are many extension projects that kind of implement that interface in a way that's specific to certain cluster computing technologies. So if you have an existing Hadoop/Spark cluster and you're using Yarn as your resource manager, you can directly deploy Dask to that cluster right now using the Dask Yarn project as an example. So if you already have a cluster up from say EMR or Dataproc, like you saw in Mariano's talk before, you can just use Dask Yarn and reuse those exact same physical resources for Dask, which is sweet. If you're working in a high performance computing cluster that's maybe using Moab or Slurm or PBS or all of these different things that I only vaguely understand that fancy scientists use, there are libraries for that too. You can run Dask on those types of clusters using Dask MPI for the message passing interface or Dask Job Queue for some of those tools like Moab and Slurm. If you are working in Kubernetes, and this can be your own on-prem Kubernetes cluster, it can be a micro-K8s cluster on your laptop, or it can be a managed Kubernetes cluster, say from Amazon or Microsoft, you have a couple of options. The Dask maintainers maintain a Helm chart that you can use to kind of Helm install Kubernetes if you want to set it up one time. There's also this project Dask Kubernetes, which it implements that interface from distributed in a way that translates into Kubernetes resources. So when you say, give me a cluster with 3 workers, Dask Kubernetes will go spin up a Kubernetes pod that represents the scheduler. It'll spin up 3 pods that represent the workers, and then it'll handle all those details like network policies for the scheduler to be able to talk to the workers. It'll manage your credentials, like all your fun Kubernetes stuff. Again, in recognition of the fact that this is the Chicago Cloud Conference, there are also a couple of options to run Dask directly on excuse me, services from the public cloud providers. So using the Dask Kubernetes project, you can directly connect to, GKE from Google, Amazon EKS, Azure EKS. Almost every public cloud at this point has a managed Kubernetes offering. You can connect to them with Dask Kubernetes. There's also a project called Dask Cloud Provider, which has non-Kubernetes options for a handful of other public cloud services. So you can use this to spin up a Dask cluster using Fargate or ECS, which are container orchestration things from AWS, or Azure ML workspaces. So there are a lot of options, and I just want to remind you again, this is the scheduler and worker. So you can also spin your own complicated kind of snowflake Dask cluster on any machines that you want if you'd like. Okay, so let's talk about how Dask does its work. So Dask work is arranged in an ordered task graph. So what does that mean? The graph part means that there's a concept of nodes and edges. The nodes in a Dask task graph are work to be done. You can think of them as like Python functions. And the edges are data that has to be passed into that function, basically. The definition of data there is a little weird. You can say that this task has to run after the other without task B actually consuming task A's kind of input. But the kind of thing to take away here is a node in the task graph is like a function call. And the ordered piece of this means that there is a notion of which things have to run before other things can run. There is this notion of dependencies. And that's the way that Dask is able to speed up your code, because it's able to take advantage of those dependencies and run independent things in parallel. And so the way that this works is in 5 stages. The first stage is called construction. And this is where you just describe your work. You just write a bunch of Python functions, and the graph is kind of created out of your functions and the data that you ask those functions to retrieve. Next is optimization. So there is a little bit of optimization. I shouldn't say a little bit. There are certain types of optimizations in the Dask graph that are done before that graph is executed. I mentioned that some of the higher level things, like my reduce by key example that you get from Spark, you're not going to get from Dask. But there is still a stage in Dask where the graph is inspected and things that are irrelevant are factored out. After that, there's serialization. So everything that you put into the Dask graph has to be written to bytes. You have to be able to put it on the wire from the client to the scheduler and from the scheduler to the workers. And that usually uses the pickle library in Python. Okay, your graph has been built. It's been optimized to the best of Dask's abilities. It's been sent over the wire to all the places where your code's going to run. The next thing that has to happen is scheduling. So in scheduling, the scheduler looks at the graph. It gets the instruction from the client to please start executing the graph. And then it looks at the characteristics of the workers and splits up that work between the workers. And then the final step is execution. So once the workers receive tasks from the scheduler, they just start doing that work. They're running in Python processes. They are loading in whatever libraries you've asked them to load in. They're doing work, and then they might be sending data to other workers. They might be sending task statuses back to the scheduler, sending logs back to the scheduler. And that is kind of how your graph proceeds. And you can monitor all of this in a dashboard that I'll show you in the second half of the talk. So if you want to just create your own task graphs, if you just want to get in and start making your own task graphs, you can use a library called Dask Delayed. So in Dask Delayed, you can use a function decorator, or you can use this kind of functional interface like this code snippet that I provided, where you take functions that you've already defined and you call them delayed functions. This means that Dask will not execute them immediately, but it'll just keep track of what data they depend on and how to call them. So for example, in this example from the Dask docs, they've already defined functions called inc, which just is increment, it's just add something, double, which multiplies a number by 2, and add, which adds 2 numbers together. And you can see like in this call dask.delayed add AB, that what we're saying is, okay, I want a delayed call of this function add, and the the inputs to this function are the results of two other delayed functions. In this way, when all of that code in the for loop is done running, none of those function calls will have been executed, but a graph like the one that you see on the right will have been created. And then it's only once you actually call a function like compute or you ask for a result of that data that all of those functions start getting called. And we'll see that in the Dask dashboard during my example. However, you do not need to be creating your own graphs by hand and thinking about the dependencies. This is really the value of the higher level Dask projects. And so the first kind of collection of things I want to talk about are the Dask distributed data structures. So there are three of them that I think everyone should know. That's bag, array, and data frame. All three of these, the kind of quick and dirty explanation is your code acts on these data structures as if it was just a single data structure in memory on one machine. And Dask handles the details of farming out operations to each of the individual pieces that are maybe spread across multiple machines. So a Dask bag is kind of comparable to a Spark RDD. It's just an array of arbitrary data. You can do functional programming things, map, filter, reduce. The Dask array tries to follow the same API as the popular NumPy project for array computing. And then Dask data frame is a distributed data frame that tries to follow the pandas API. And you can see in this diagram that I borrowed from one of the Dask maintainers how this is working. So in a NumPy array, you can see those like 6 blocks and you just call sum and you get the array, right? In a Dask array, you write code against it as if you had all 6 of those little blocks in memory. But the reality is that Dask array is actually made up of many smaller NumPy arrays. And when you call an operation like sum, what'll happen is Dask will say, okay, each of those chunks, which might be on different workers, I want to call sum on that, and then kind of combine the results and call sum at the end. So for those of you who've worked with Spark, these concepts should be familiar, but the important point to take away here is that you don't need to, with these objects, you don't need to think about the fact that, this can be broken down into like some sort of, map and reduce operation. You just write sum and you get an answer back in the client, which is sweet. Okay, building on top of that, Dask also has this ecosystem of machine learning libraries which know how to do distributed training distributed training on these Dask data collections so that you can train a model on a data set that doesn't fit in your laptop. The one that's maintained by the Dask maintainers is called Dask ML. So Dask ML implements some common machine learning algorithms. It has equivalents to the scikit-learn pipeline operator, the column transformers, grid search CV. So you can do things like have a data frame that is actually split across multiple machines and do feature engineering where you're just adding columns to that data frame in a distributed way so that on each individual machine, those features are added to that chunk of the data frame, but you never have to hold the whole thing in memory. And then there are other projects that try to kind of connect Dask's model for parallelism with those distributed training frameworks that I talked about before. So for example, for Dask XGBoost and Dask LightGBM, these have interfaces to XGBoost and LightGBM, which can take in a Dask array or a Dask data frame, these distributed data structures, but then know how to, on every worker that's running a Dask worker process, they'll also run like an XGBoost worker process or a LightGBM worker process and do distributed training. So this is just, one of the ways that Dask allows you to throw hardware at a machine learning problem to bring down your runtime or to increase the space of which experiments you try. Okay, I'm gonna take another sip of water and then we're gonna go do a live demo. Okay, fantastic. If we were live in person, I would have said if you ask a question during the demo, I'll give you a Dask sticker, but that's what you lose with digital. Okay, so let's do some stuff. So what I'm going to show you next is an example of working with Dask for machine learning. So we have this data set. You probably have seen other benchmarks and other tools with it before called the New York City taxi data set. This is a data set where each observation is one ride in a New York City taxi. And there's information like the time of the ride, how much the tip was, how much the total amount was. I'm going to pull in some of this data from S3. This data lives in a couple hundred CSVs in S3 in a public bucket. And what I'm going to do is try to create a Dask data frame out of that data and then train a couple machine learning models on it. So let's get into that. And all of this code, by the way, if you'd like to follow along or if you'd like to look later, is on my GitHub at github.com/jameslam/talks. And it's this one called Dask Machine Learning. So I just pushed it, fairly late last night. I finished it up. So you can go look at this code there as well. And this will all work as long as you have an AWS account. This will all work. Should work beautifully for you. There's nothing proprietary here. Just be really sure to shut everything down when you're done. Okay, so let's talk about the libraries that I'm bringing in. Actually, let's start up the cluster and then we'll talk through that stuff. Okay, so the important things to think about here. I'm bringing in a library called Dask Cloud Provider. This library is going to allow me to create a cluster out on AWS Fargate, which is a container orchestration technology. So the scheduler is going to be a container running in AWS. Each of the workers is going to be a container running in AWS. I'm also bringing in this distributed library that we talked about before. So this client class is going to be the Python object that I use to talk to the Dask scheduler and tell it to do things. I'm bringing in a couple of libraries from scikit-learn. So again, these are not parallelized by default, but these are going to be a couple of helpful interfaces for us. And then I'm bringing in some of these tools from Dask ML. So for example, for those of you who've used scikit-learn, these names like column transformer, standard scalar, grid search GD, these might look very familiar to you. In Dask ML, these have the same interface as the equivalent functions in scikit-learn, but they know how to take advantage of Dask to do their work in parallel. This is just typical boring hard coding column name stuff, not that interesting. Okay, so let's talk about what's happening here. I'm creating my Dask cluster, and I'm going to create that out on Fargate. So if I go to the ECS console, oh no. I was all signed in. I thought I was so smart. Give me 1 second. I hope everyone is giving me a lot of credit for using two-factor. Okay, fantastic. Okay, fantastic. And I'm in the wrong service too, which is great. All right, let's go to the Elastic Container service. And what you can see is this cluster has been created. I did not pre-create this. This is being created by the Fargate cluster class from Dask Cloud Provider. The way that ECS works, if you've never used it before, is that you have this concept of tasks. Tasks are just like, think of each of these as one running container, basically, for simplicity. And what you're going to see here, if we look at these names, is I have 1 scheduler and 6 worker tasks. So that is exactly what I've asked for here. So what I've told this Dask Cloud Provider library is, okay, all of these use this public Docker image from Dask. I want to give them, this is 30 gigabytes of memory. This is the most memory that you can give to an ECS task. I've asked for 6 workers, so I'm going to get 6 machines that are, 6 containers that are each running this image with this much memory. I've made sure that everything is public resources. This is just a conference talk. I don't need to care about like keeping these locked down. You can get much more complicated with this. You can put things in your own VPC. You can, control the permissions, but it's a conference talk. Like, let's just make it work. The scheduler timeout says how long, if I take more than 45 minutes to send the scheduler any work, it will shut itself down. So this is a cost control measure. And then this environment variable, I'm saying, hey, when you build this container from this image, I actually want a couple of other libraries. And so what you can see here is that now that this is done, printing this cluster object in a Jupyter notebook will give me this little widget with a Dask dashboard. So let's go look in ECS first. And sometimes you have to refresh with the Amazon console. There we go, everything's running. And I want to show you a couple of things in the Amazon console first. So just using this function call with Fargate cluster, we have all these tasks running in ECS, and now we can go look at some cool stuff. So for example, let's go see what the scheduler's been doing. We can not click on that because that was the wrong thing. We need to go to, sorry. We need to go to the task. There we go, not the task definition. And we can see all of these logs. So all of these logs are being written to CloudWatch logs. This is the log from the scheduler task. So what we can see is here's a worker joining and saying, hey, you can send me stuff, I'm here. Here's another worker joining, hey, you can send me stuff, establishing some connection. All of this, installing collected packages, all this garbage. This is because I asked for those extra libraries to be pip installed when running this container. So this is just all like pip install log stuff. And then a couple of extra logs from that container. And there we go. So as we work here, if we want, we're going to be able to have we're going to be able to look at all of these logs in CloudWatch. If we look at the worker logs, I think you'll see they're not really as interesting yet because we haven't done very much. The worker's just saying, hey, I set up this local directory for whenever I need to write stuff to disk. I'm running a Dask worker process with 4 threads. I have 30 gigs of memory available to me. And then the Dask worker, you're seeing this process called the nanny process. So this is a process that kind of, it takes care of the Dask worker process. It nurtures it. When the Dask worker process fails, this nanny process will know that and restart it. And so in that way, you get a little bit more resilience if your work happens to blow out the memory in a worker process or something like that. Let's go to the Dask dashboard. So remember I asked for 6 workers. There's nothing going on this screen that I'm on because we haven't asked the cluster to do any work yet. But if I go look at the workers, I can see what they're doing. Their CPU is pretty low, but it's like kind of ticking around. This is just them checking in with the scheduler saying, hey, is there anything to do? Like, what's up? I'm not busy right now. You can also get this nice total view that tells you, okay, we have 168 gigs of memory available to us across the cluster, and most of it is not used right now. This dashboard will be more interesting once we start doing some work. So back in Python, we can look at some details about the workers. This is just a gnarly JSON, but you can see a bunch of stuff. We can see, what address is each of these workers at, what address is the scheduler running at, where is this dashboard link, all kinds of interesting stuff like that. We don't really need to dig too much into that. But one really, really powerful feature of this distributed cluster is that we can scale it up and down programmatically. So remember that I requested 6 workers. I actually want 2 more workers. So I'm going to run cluster.scale. That returns immediately. You notice the cell is already done because this is an asynchronous call. If we go to the ECS console, we should see these 2 new tasks that are in provisioning. So this is 2 new workers that are spinning up. We do not need to wait for those workers to spin up to keep doing work though. So let's just go do some stuff. Next, I'm going to read in some data into a Dask data frame. So all of this is just like hard coding the names of files and stuff. Not that interesting. But let's talk about this Dask data frame code. So this read CSV, it has the same arguments as pandas read CSV. And what I'm saying is I want you to create a Dask data frame for me from this list of files in this S3 bucket. These are the columns that should be interpreted as date times, not as strings. This is just saying this is a public bucket, so don't throw weird Boto3 errors when I try to do stuff with it. It's a public bucket. And then this is saying the columns to select. And then to make this example run really fast just for the time of this talk, I've sampled down to 1% of the full data set. And notice that this call returned immediately. So the Dask data frame right now, if we look at it, there's no data in here yet, right? This tells me, okay, I'm going to be reading 148 files. I haven't given it an index, so each file is going to be its own partition. Here are the columns. I know the types. It's able to kind of peek ahead and know some things about that. But nothing has been read yet. If we go look out on the cluster, oh, look, our other 2 workers have joined. Welcome to the party. If we go look out on the cluster, right, they're all hanging around 100 megabytes. So nobody's actually read any data yet, but we've just defined this Dask data frame. This goes back to what I was talking about before, how these Dask higher level collections, they are task graphs. So right now you should, if we dug deep enough down here, we would find a Dask task graph that's ready to be augmented and submitted to the scheduler. So let's do that. Let's count the number of rows in the data frame. So think for a second about what this is going to have to do while we watch it happen. So to count the number of rows in the data frame, you can see these 2 tasks here. One's called len chunk, one's called get item read. So think about what's happening here, right? Each file has to be read. The number of rows in that file has to be computed. And then there's going to be this final step that is add up all the number of rows from all the chunks, and that's going to be the total number of rows that the entire data frame has. And so we can see in the Dask graph, the Dask dashboard, how this is going. The tasks are kind of proceeding. We can look at the graph. Oh, good, I caught it just in time. So you can see we have all of these get data things. Each of those tasks maps directly to one, tell me how many rows are in that chunk task. And then all of the results of all of these have to come together in this task that says count up all the rows from all of them. And now we're done. Let's go back and look. Okay, so we have about 1 million rows in this smaller data set that I've sampled. Let's look at another kind of more complicated one. Next, I want to see the size of the data frame. So what I'm going to have to do is for each chunk of the data frame, I'm going to have to compute how much memory it's using. So let's go look at that. That one's going to be fun. Oh yeah, look at this. So we've got some code that is reading in each chunk. We've got some code that's kind of doing a group by operation where we're saying, okay, we can start combining some of those sums together. These task names don't always totally make sense. There's other considerations here, like making them unique that make the slugs maybe a little bit difficult. But you can see here as we watch, I can see the tasks. I can see the task graph. Did it finish right when I clicked that button? Yes, it finished right when I clicked that button. We could have seen the task graph. That's okay. We'll see more. And then you're able to monitor the workers as they go and see, okay, what's happening, which ones are working hard, which ones are running out of memory, stuff like that. Okay, so like I mentioned, Dask data frames are lazily evaluated. So even though we've just asked for those two answers, the data frame is not just sitting out in the cluster right now, because that would be very memory inefficient if all we cared about was stuff like the number of rows. So for the rest of this, I want to be sure that the whole data frame is permanently materialized in the cluster. This is kind of similar to how you can call the cache method on like Spark data frames or Spark RDDs. So I'm going to run this method persist, and this returns immediately. This is also asynchronous. This just generates a task graph where each task is like, go get some data. And I'm going to use this wait function from distributed to make sure that nothing else continues until the data frame has been totally read. So we can go back. All right, now we're doing stuff. Look at this, 200% of CPU. And we can go look at some stuff. So you can see we have 148 CSV files to read. Because I'm using this sample down to 1%, there are 148 tasks that are get a file from S3, and 148 tasks that are sample down to 1% of that file. We can look at the task graph, and you can see there's no sync at the end here, right? There's just, for each file, there's a read and a sample. And then once these are there, let's just start watching. Is this already done? That was fast. Okay, if you had seen before, each of these was hanging around a little bit under a gig of memory, and now they're at between 1 and 2 gigs. So our data set is now permanently cached out on the cluster. And what that means is if I run this, how many rows are in my data frame function again, it's going to complete immediately. So remember when we did this above, this took almost a minute to complete. On the same data set, same number of rows, this took, basically no time because the data is already there, because Dask didn't have to go read all that stuff back in from S3. So, okay, that's sweet. Now let's do some machine learning. So what I want to do is add some code that'll just create a couple of different different features. And notice all this code just looks like Pandas code, right? There's nothing Dasky about this code. It's saying, add this column called tip fraction by dividing these two columns. But all of these things will be evaluated when we get to the point of evaluating them. All of them will be evaluated in parallel out on the different chunks of the Dask data frame. Okay, and this returned immediately because again, Dask data frames are asynchronous. I'm going to keep repeating that. So this function call over this data frame, it doesn't actually return anything until we ask for more details. So I'm going to do a very small grid search. I'm going to look for the best set of hyperparameters for a random forest regressor to predict the tip amount from these rides. So the tip amount is, it's the tip fraction, excuse me. So it's like the proportion of the total fare that is tip. I'm going to search over a small grid, so 2 different values for the number of trees, 2 different values for the maximum depth, that controls how the trees are grown. But what you can see is I can organize all of my stuff just like you would with scikit-learn code. But each of these functions in here, like the dummy encoder, the column transformer, grid search CV, these are Dask versions that will take advantage of the cluster. All right, this is going to be really fun. Let's do this. Oh yeah, look at that. So we've got all kinds of stuff going on here. Each of these functions, these are different feature engineering functions. Get item is a call where the workers are passing data between each other. We're sampling that data. We are doing some adding and subtracting of stuff. We're doing all kinds of cool stuff here. And then you can see that everything has kind of stopped, right? That there's this synchronization stage. And that's just based on the algorithm that I chose here. The way that works is if we watch the workers, see how there's like 2 or 3 workers that are clocking at all of their CPU and everything else is just sitting there. That's just an algorithm choice on my mind. Like the one that I kind of decided to use for this example is not completely parallelized across the whole cluster. So there are still some opportunities for improvement there, depending on the algorithm that you want to use. But hopefully what you can see, is we are making progress here. A ton of different stuff was done in parallel, especially all of that feature engineering stuff. And then I expect this will take like maybe another 2 minutes to finish the scoring run. So while it does that, let's take a look at some stuff. The graph for this one is really fun. So each of these columns is a different class of thing, which is cool. What else do we have going on here? We've got some random forest regressor fits. So there's 12 of these because we searched a grid of 4 possibilities and we did 3-fold cross-validation. So there's 12 model fits that have to happen. And you can see that the tasks will be labeled as being, waiting on something, processing, which means like they're in progress. The red means memory. It means like this task is done, but its result is still in memory because it's needed by something else. If we go look out on ECS, we can go back to our worker logs and let's see what they say. While we wait for this to run. And the workers should be doing some stuff. I guess they're not logging that much stuff. Okay, that's fine. They're entitled to that. We can go back to status here. Doing well, doing well. So we have 1 more model fit left. So can you see this one worker is on 100% CPU. It's just like finishing up that last model fit and then we are gonna be good. And look at that, everything's done. Looking great, looking great. Yeah, this is the part of the talk where I just point at things that I haven't explained and mutter, so I hope you're really enjoying that. But we should almost be done here. And let me explain the final thing that we're gonna do. So in grid search CV, the goal is to train a model on the same data set with different combinations of hyperparameters, and then to choose the best model based on a metric, where that metric is evaluated on a holdout data set. So when we say CV equals 3, that means you're doing something called cross-validation, where you're saying like breaking the data into 3 pieces, train a model on 2 pieces, predict on the 3rd, et cetera, et cetera. So as soon as this completes, we're gonna get back the best set of parameters and the best model, and all of this kind of best parameters, best score, best model, these are no longer gonna be Dasky. These are gonna be scikit-learn models, sets of parameters that you can take and deploy into however you deploy scikit-learn model objects today. If this task ever finishes. Come on. It's taking a little longer than I expected. I apologize, but it's okay. We have a couple minutes, and this is the last piece of this. Just this one